Okay, here's part two of a Unit R review. This should be pretty quick. Okay, I wanted to just start this one by showing you how if you take a 1 volt divided by 1 Henry, that indeed you do get 1 amp per second. So I want to show you that. And the way I'm going to show you that is remember that like 3 Henrys, what 3 Henrys means, if you have an inductor that has 3 Henrys of inductance, what that means is that for each 1 amp per second of current change, in the inductor, there will be 3 volts induced. Don't ask me why I put this here. That's a mistake. This is a mistake. So for 3 Henrys means that for each 1 amp per second of current change in the inductor, there'll be 3 volts induced. Okay, so another way of writing that is that 3 Henrys, that's the same thing as you get 3 volts for each 1 amp per second of current change. So do you see how if I take volts and divide it by Henrys, well, this is a Henry, it's a volt times amps per second. Well, the V cancels out and the amps per second come to the top. So sure enough, you get amps per second. Okay, let's go on to this guy. With this one, could you tell me, here's 8 volts, 6 ohms, 4 Henrys, and another 2 ohms. These are all in series. At t equals 0, could you tell me when I close this switch, can you tell me what the current in the battery is going to be at t equals 0? What will be the current in the battery? That's a lowercase I in the battery, B in the battery. And then what will be the EMF that's induced in the inductor? Okay, go ahead and pause. Okay, so at t equals 0, as soon as you close this is going to act like a battery pushing this way. And the current is going to grow. It's going to grow like that. But if you look at our graph at t equals 0, you see how if that's I and t, see how at t equals 0, that's 0? So that means that there's no current in here. Now, if there's no current here or here, then you got 0 volts, because I times R, there's I times R, so that's 0, and that's 0. So this has to be 8 volts or negative 8 volts. It's going to be 8 volts in that direction. Not that voltage is a vector quantity, but it's going to be pushing the other way. Okay? All right, then a long time later at infinity, at t equals infinity, or at least, a minute later, then could you tell me how long it's gonna, what the answers to these will be? So what will be the I through the battery, and what will be the EMF induced in the inductor? Okay, so a long time later, this is going to behave just like a wire, because look what happens to the current. The current is flattening out, and so the slope of this graph is going to 0. And remember that this EMF is L di dt. And so this is going to be just like a wire. So what we have is 8 ohms of total resistance and 8 volts. And so we're going to get 1 amp there. And then the EMF that will be induced will be 0. Why? Because it's negative L di dt. And look at di dt. Look at the slope right there. If that's not pretty close to 0, then see how it's so flat? All right. Next question. I have a 12 volt battery, a switch, a 4 ohm resistor, a 2 ohm resistor. Let's make this 1 Henry. And this is a 2 farad capacitor. Okay, the instant I close this switch, could you tell me what the I through the battery will be? What will be the I through the battery at t equals 0 when I close this switch? What will be the I through the battery? Okay, I hope you tried that. Okay, when you close this switch, this is not going to, at t equals 0, this is not going to let current flow through it. It's going to push that way. And so, I mean, eventually current will flow through. I mean, the graph of this inductor, the I through that, is going to, it's going to grow. But at t equals 0, there is no current going through there. It's all pushing that way. Okay, so if there's no current flowing through there, then all the current has to be flowing this way. Now, you're wondering why current can flow through in a capacitor. Capacitors behave just the opposite of inductors. At t equals 0, they act just like a wire. They flip-flop. At first, this acts like a battery pushing this way, and this acts like a wire, and then afterwards, this will act like a wire, or excuse me, a battery, and that will act like a wire. And so, let me explain why this acts like a wire. At t equals 0, putting charges down there, charges don't go across. They don't go across the capacitor. But they do go onto the plate, and when it's not charged, it's very easy for those charges to file in and set up on the capacitor. It's just like it was a wire at that point. As soon as this starts to get any charge, though, the charge starts to push back, and so we can expect this capacitor to start pushing back as soon as it starts getting a charge on it. Okay, so this is going to have 0 volts across it because it's not charged. If that is 0 volts, then Kirchhoff's loop rule would say that this has to have 12 volts across it. And so 12 volts divided by 2 ohms is 6 amps. So it's going to start out at 6 amps. The I through the inductor will be 0 amps. Okay? The I through the 4 ohm will be 0 amps. Now, what will be the voltage across the inductor? Well, the voltage across the inductor, since there is no current through here, there's no voltage, it's got to be 12 volts. So this is the voltage across the inductor at t equals 0 will be 12 volts, or negative 12 if you want. Okay, a long time later, at t equals infinity, or several minutes later, what will be the new answers to these? What will be the I through the battery? What will be the I through the inductor? And what will be the EMF of the inductor? Go ahead and pause and see if you can get it. Okay, we're back. Okay, so the I, this is now fully charged. So it's like a no vacancy hotel. It's no longer accepting electrons, and so nothing's going that way. So the voltage here is 0 volts a long time later. So then I know that the voltage across here is 12 volts because of the loop rule. In fact, I could tell you the charge. I should have asked the charge on here. The charge is going to be 24 coulombs. I'm using huge numbers here. These numbers don't normally get this big. I'm just making it so that it's easy to use. These numbers are just a little bit wacky. Okay, just because you don't normally get a 2 farad capacitor. That's a huge capacitor. Okay, what will be the I through the battery then? No I's going this way. All the current's going this way, and we have 4 ohms of resistance, so that's going to be 3 amps. There'll also be 3 amps in the inductor because they're in series. What will be the EMF of this thing, of the inductor? It's going to be 0 volts. What will be the voltage across the capacitor? The voltage across the capacitor, I already mentioned, it's going to be 12 volts. Okay. All right. That's about it. I was going to ask you maybe the period of this circuit, and I'm out of time, but the period of this circuit, and you could ask a bunch of other things about the initial current and the period of this circuit and the maximum voltage and all that good stuff. So, but I'm not going to do that. But you can just guess what you would say to all these things. What would be all the maximum current, the maximum voltage, and so on. All right, bye.